So we've started building Lewis structures, and now we're ready to start doing things with. What kind of information can we obtain from a Lewis structure, and how can we modify these to be more accurately a depiction of the molecule itself? Because sometimes we can draw a Lewis structure and it obeys all the rules, but it is not an accurate depiction of the molecule, and then it's useless. Why in the world would we want a Lewis structure that didn't depict in some way what the molecule is doing itself? So what we got to do is something called formal charge. Now, formal charge is not a real charge. We've talked about real charges. We know that when something accepts an electron, it gets negatively charged. When it donates an electron, it's positively charged. We've talked about partial charges in terms of something not sharing equally and setting up partial charges. But formal charge is not a real charge. It is nothing more than a bookkeeping device for our atoms within a Lewis structure. So we're going to have to keep that in mind while we use the word charge with it. It's not real, it's bookkeeping. It is a means by which we can make judgments about our Lewis structure. Okay, so what's a formal charge? Well, first of all, why would we have to have a formal charge? The reason that you would have to have a formal charge is sometimes you can do a Lewis structure like I suggested, and they be completely different from each other, and you're trying to decide which one is a better representation of your molecule. Sometimes you can use formal charge to, if the connectivities is kind of confusing to you, you can use it to help you figure out how things are connected. So what is a formal charge? Here's the definition. It's a charge it would have if the bonded electrons were shared equally between the atoms that are bonded to. Okay, so that's what it's all about. It would have if all the bonded electrons were shared equally between them. All right, so this is how you determine a formal charge. Reminder, it's just a bookkeeping device. What we're going to do is we're going to go to the atom in the Lewis structure, and we're going to see this atom, how many valence electrons does it bring to the party, okay? How many valence electrons does it have off of the periodic table? And then we look at how many electrons are surrounding that atom. Lone pairs count towards that atom, and bonded pairs only count one per in that atom. So they're doing this, okay, I have two electrons. Let's just do what I mean here. Okay, I have two atoms, they are sharing these electrons. I'm going to count, and I'll draw them like this. These are two electrons, right? This guy counts towards this guy, and this guy counts towards this one. And that's what I mean by you're going to count lone pairs and one half the bonded electrons. So you only get one going to this one and one going to that one. The easiest way for me to explain what I'm talking about there is with an example. So we're going to do an example of Cn minus. Cn minus. Now we're going to go ahead and review the process of doing a Lewis structure with this one here. Carbon has 4 valence electrons, nitrogen has 5, and then there's one more electron for that minus charge. I have 10 electrons to work with. I put the atoms down. I have carbon, I have nitrogen. Got to make this thing right a little bit better. All right, reset. I have carbon, I have nitrogen. I start with a single bond. Okay, that's 2, and then I come over here, 4, 6, 8, 10. I have to stop. I've used all the electrons I can use here, and now I start shifting. So I'm going to take these 2 and put it right here, and that brings it still at 8, but this is coming up to 6. I'll do that again, and this is just like the N2 molecule that we did before, but this guy has an overall charge of -1. So there is its Lewis structure. So how do we do a formal charge? Okay, so we're going to do it for each atom in there. So let's do it for carbon first. We go to a periodic table and look at a periodic table, and I think I've got one right here. Yeah, we find carbon. There it is. Okay, and we see that carbon has 4 valence electrons. We knew that already. That's what we counted here. So that's the first number. That's coming off the periodic table. Now what we're going to do is we're going to subtract the lone pairs in their entirety that are on this carbon. So that'd be 1, 2. And then you subtract, or you're also going to count up 1 per bond. So that's what I meant by 1/2. Let's look at that statement there. 1/2 the bonding electrons. There's 6 bonding electrons there. Carbon has 8, but we're only going to, for our bookkeeping, count 1 per bond. So we have 1, 2, 3, 4, 5. So we would subtract 5. And that gives me a -1. 4 minus 5, the minus 1 for that. And then we come to this nitrogen here, and we look at the periodic table, and we know it has 5 valence electrons. And we have 1, 2, and 1 per bond, 3, 4, 5. 5 to subtract from it, so that gives me a 0 formal charge for this guy. So that's how you count up formal charges. Now sometimes, and they'll do this a lot of times in organic chemistry, your next sequence of classes, they will take that formal charge and they will write it above the atom with a circle around it. That represents that it's not a real charge, it's a formal charge. Sometimes you'll put a 0 to represent a no formal charge there, but they don't always do that. All right, so I'll get rid of that little guy right there. Okay, so that is how you do a formal charge. Now, these are some things that should happen when we do a formal charge. For a neutral molecule, if you took all those formal charges, they have to add up to 0. Okay, if you've done it right, the formal charges will add up to 0. The next thing is, if you have an ion, which is what I've got right here, those formal charges have to add up to the overall charge of the ion. So there we have a -1 sum of my formal charges. That adds up to the overall charge of the ion. So that is correct for that. And so we just did. We looked back and we saw that this is true for our example. All right, one more time. Formal charge does not represent a true charge, okay? It is nothing more than a useful bookkeeping device that you haven't learned anything about its usefulness yet. You're just learning how to do it. All right, so let's practice some more, all right? Formal charges on NO3 minus. So NO3 minus, okay? We had done a Lewis structure, and you worked on doing that in our last lesson. So let's just go ahead and write what we had come up with on our last lesson. We had nitrogen, we had one of them being a double bond, the other two are single bonds. We give everybody the right number of electrons that they were supposed to have. This is the Lewis structure of NO3 minus, okay? So I'm remembering that from the last time we did it. Now we're ready to do formal charges. So let's do this oxygen first. We look at the periodic table, and we know that oxygen will have 6 electrons from the periodic table. Then we count all of the lone pair electrons, 1, 2, 3, 4, 5, 6, and 1 per bond. So we are going to subtract from that number 7. This guy has a -1 formal charge. Every oxygen that looks like this, meaning has the 6 valence electrons and a single bond, would have the exact same formal charge. So this guy is also going to have a -1 formal charge. It's still going to be 6 minus 7, so it's got to have the same thing. This one looks a little bit different, so it's going to have a different formal charge. So let's do this one here, okay? Oxygen has 6 valence electrons. That's not going to change. We count these, 1, 2, 3, 4, and 1 per bond, 5, 6. We subtract 6, and we have a 0 formal charge on that oxygen there. And every time oxygen has 4 valence electrons, 2 lone pairs, and 2 bonds, it'll always have a 0. After you've done these for a while and you've looked at oxygen for a while, as soon as you see that, you're going to know it's 0. As soon as you see an arrangement of oxygen like this, you're going to know it's -1. But I wouldn't want you to memorize that. I mean, if it sticks in your head and you can't let go of it, that's fine. But I want you to know how you get that number. All right, the next one is nitrogen. You can do a formal charge for every atom. Nitrogen. If I look at the periodic table and find it, I see that it has 5 valence electrons. Now I'm ready to count. Lone pairs, there are none, and 1 per bond. 1, 2, 3, 4. So I subtract 4, and that is going to give me a +1, okay? So since it's a charge, even though it's a formal charge, we add the symbol, pluses and minuses, to go with it. Now, like I said, sometimes what you will see is they'll put the formal charge with the atom, with a circle around it. So those are the formal charges. Now, do the sum of each of these formal charges add up to the overall charge of the atom? Yes, -1, 2 -1s, and a +1 gives you a -1 overall. So that is correct. Now let's do the carbonate ion, CO3 2-. Okay? If we're going to count up valence electrons, we're going to have 4 for carbon. We're going to have 6 times 3, that's 18 for oxygen, plus 2 more, and that's 24 electrons to work with. That's exactly the same thing we had over here. So we've got exactly the same look of a Lewis structure. That part's not changing anything because this is how you get all of those guys. Now, you don't have to know that that is what it looks like. You can go through and you can follow all of your rules just fine to do that. But the overall charge is 2 minus. So the formal charges have to be different because the overall charge over here was a -1. And now the overall charge is going to be a -2. Now I'm going to put a little lines around here so it doesn't look quite so confusing with all my other work. We're focusing on this little box right here. Let's do formal charges, okay? So oxygen has 6 valence electrons. We subtract for the lone pair 1, 2, 3, 4, 5, 6, and 1 per bond. Subtract 7. There it is, -1. Oxygen with a single bond is going to be -1. Oxygen with a single bond is going to be -1. Oxygen with a double bond, well, if we remember it, fine. If we don't, we figure it out. 6, 1, 2, 3, 4, 1 per bond, 5, 6. It's 0. So there's its formal charge. Now let's do carbon. Carbon has 4 valence electrons, and we subtract, there's no lone pairs, we subtract 1 per bond, that's 4 to subtract, and that's a formal charge of 0. Now we have a -1, a 0, a -1, and a 0. Add that all up, and you've got a -2. So those are the formal charges on the atoms of this carbonate ion. All right, for what do we use formal charges? Why in the world would we use formal charges? Well, sometimes you can draw more than one Lewis structure that obeys the octet rule, and you're going to try to figure out which one is better. All right, so sometimes you can do that. Sometimes you're not sure of how things are connected. So you're not sure what atom is connected to what. On that first slide, when we're learning how to write Lewis structures, I said decide on the connectivity and put the least electronegative atom in the middle. Sometimes you can follow all those rules and you still don't know how they're connected for sure. So you'd try more than one way, and whichever one gave you good formal charges would be the better Lewis structure. So it is really got the job as a bookkeeping device to help us figure out the most plausible structure, whether it has to do with connectivity or whether it has to do with a Lewis structure where more than one obey the octet rule. Now, in terms of this, there's some things that you have to know. Here we have a bunch of formal charges. How do they tell us anything about the Lewis structure? Well, there's some rules that we find out in terms of drawing a Lewis structure and doing this bookkeeping. Certain formal charges are better than other formal charges, so we have to look at the rules here. So let's just kind of go to their screen and walk through these a little bit. So whenever you've got a neutral molecule, okay, so we're not talking about polyatomic ions. If you could have a Lewis structure where you have no formal charges, what does that mean? Formal charges of 0 all across the board, then that would be the better Lewis structure if you had more than one to choose from. But if you're dealing with, you don't have that as an option, then you're always going to look for the smaller formal charges. So small formal charges are going to be more favorable than large ones. So you're looking for zeros, ones, plus and minus ones, and not things that have plus and minus twos or plus and minus threes. You would want the smaller formal charges. Now, if you have two Lewis structures and they've satisfied this, they both have the same numbers for their formal charges, you're going to want to find the Lewis structure that puts the negative formal charge on the most electronegative atom, okay? And so you might be able to draw more than one Lewis structure. They're both got zeros, ones, and minus ones, but you want to put the minus on the most electronegative atom. So you know that electronegativity increases as you move to the right on the periodic table, increases as you move up, and that fluorine is sitting up here as the most electronegative of the bunch. So that will be the last thing that we'll use to help us guide what is the better Lewis structure. So we're going to do SCN minus, and we're going to see how many Lewis structures we can draw for it, and then we're going to use formal charges to help us select the best one. So we know that for this, the connectivity is as we see it. The S is connected to the C is connected to the N. Okay? Counting up valence electrons, if we go to the periodic table, sulfur has 6, carbon has 4, nitrogen has 5, and this thing has an overall charge of a -1, so I'll add 1 more for that. So that's 16 electrons that I'm working with. So I will come over here and I will start with single bonds, 2, 4. And then I go to the terminal, the outside atoms, and start obeying the octet rule until I've used 16 electrons. So I've used 4, and I'll go over here and do 6, 8, 10, go over here, 12, 14, 16, and I have to stop because I've used my 16 electrons. So I'm stopping here and I look at it and I see that this carbon is nowhere near happy. He only has 8 valence electrons. So this is where we start shifting. So if I take 2 electrons from here and pull them into here, now the sulfur didn't change how many he had. He still has 8, and that brought carbon up to 6, and that's still not quite there. So I like symmetry, so let's take it from this side and then we'll have that there. So now I've got the carbon satisfied. I've still used only 16 valence electrons. Everybody has 8. I would, in good fashion, put square brackets around it with a minus out here, and that is 1 Lewis structure. Now a lot of students say, oh, that's it. That's all there is, because I've brought 2 in here, 2 in there, and there's nothing else I can do. But there are any opportunities of sharing where I have 4 bonds would be a good Lewis structure. So I could have done it this way. Now let's start back with what we had that we started to needing to do the shift. We had this looked like this, okay? This is where we were. And when we shifted, we started by taking 2 right there and moving it in here. There is nothing that says we can't take 2 from here. Did that not keep sulfur satisfied and make carbon happy? And nitrogen is fine with that. So that is another possibility. Okay? And then we could have said, well, what about this? We'll start again at the same point that we were. Okay, we had single bonds. This is where we had first used our 16 electrons and realized that carbon wasn't happy. Why not make nitrogen do the sharing, okay? So nitrogen would say, okay, you can have 2 of my electrons. Carbon says, I'm still not happy. So he says, okay, you can have 2 more of my electrons. And now we have got carbon satisfied, nitrogen satisfied, sulfur satisfied, and this is a Lewis structure. So I have 3 Lewis structures. Every one of them obeys the octet rule, but they're very different. This one has 2 double bonds, a triple and a single and a triple. Completely different ones. And the question is, all right, is one better than the other? And that's where formal charges come into play. We start doing formal charges, and they will help us determine whether or not one is better than the other. So it's our bookkeeping method for this. We look at a periodic table, and sulfur has 6 valence electrons. We subtract the lone pair, 1, 2, 3, 4, and 1 per bond, 5, 6, and that gives us a 0 formal charge. We look at our carbon. Our carbon off the periodic table has 4 valence electrons. It has no lone pairs. I count 1 per bond, 1, 2, 3, 4, and I have a 0 formal charge. I go to my nitrogen. Off the periodic table, it has 5 valence electrons. I count up the lone pairs, 1, 2, 3, 4, 1 per bond, 5, 6, okay? It's a -1. I do a double check. Do these add up to the overall charge? Yes, they do. So those are the formal charges on that one. They don't look bad, but I don't know if they're the best. I come to this structure. Sulfur has 6 valence electrons. I subtract 1, 2, 1 per bond, 3, 4, 5. I'm subtracting 5. So I have a +1 formal charge. I come to my carbon. It had 4 off the periodic table. 1, 2, 3, 4. That's 1 per bond. And I have a 0 here. I come to my nitrogen, 5 off the periodic table. I count up the lone pair electrons, 1, 2, 3, 4, 5, 6. Add 1 per bond, that's 7. And I have a -2. Now when I look at these two, I can already say that one is better than the other. It's not because it's symmetrical. That is not why it's better. It's because of the formal charges. Low formal charges are better than higher formal charges. This one has a 2 in it. This one did not. They still add up to the overall charge, which they should always do that, or you made a mistake in calculating your formal charges. But this one is better than this one. So I could probably eliminate this guy. And then I come to this one. I don't know that this one is any better than this one. So now we'll do our formal charges again. Sulfur off the periodic table has 6. We subtract 1, 2, 3, 4, 5, 6, and 1 per bond, I subtract 7. So I have a -1 here. Carbon has 4 off the periodic table. I subtract 1 per bond, and so I'm subtracting 4. And I have nitrogen. Oops, I don't know why I'm writing nitrogen again. Let's just erase that there. We have nitrogen with its 5 off the periodic table. I have 1, 2, and then 1 per bond, 3, 4, 5. I subtract 5, and I have a 0. These add up to the overall charge, so I know those are decent formal charges. And now I look at these formal charges versus these formal charges. See how they both have 0, 0, -1, 0, 0, -1. So I can't eliminate one or the other with that second rule. Look back at those rules. We've got that zeros across the board are best, but I can't have that if I have a charge here. We have that low formal charges are better than big formal charges, so we've eliminated this one. And then there's a third one. The third one says find your negative formal charge. So I have a -1 here and I have a -1 here. And you want the negative formal charge on the most electronegative atom. So if we look at a periodic table, and let's see if I've got one nearby. Oops, not that direction, maybe the other direction. Nope, not that direction. Well, dang it, I've got one eventually. Sorry, there you go. We find nitrogen and we find sulfur on our periodic table. So here's the nitrogen, and here is the sulfur. Okay? Now it's kind of hard to distinguish between which one's more electronegative between those two, because we know that as we go to the right, sulfur is farther to the right and electronegativity increases as you go to the right. But we also know that if you go up, electronegativity increases when you go up. And so nitrogen's above sulfur and sulfur is farther to the right. But the fact of the matter is there is a bigger increase in electronegativity when you move up the periodic table. And there's not as great or a drastic a change as you move to the right. So that makes nitrogen the more electronegative than sulfur. These elements across the top here are the most electronegative, and then we can throw in our chlorine. So even though sulfur is further to the right, it doesn't trump the fact that nitrogen is higher, and this group up there is the most electronegative. So nitrogen is more electronegative. So we can turn back to our light board again and then examine these two, and we've got nitrogen having the -1 formal charge, sulfur having the -1 formal charge. So that makes this the best Lewis structure of the three. Now if I did a minor change between these, and my minor change is going to replace all of the sulfurs with oxygen. See how oxygen is just right above sulfur on the periodic table? It would have the same number of valence electrons. It would have exactly the same 3 resonance structures that could be drawn. So I'm just going to go in here and replace the sulfur with a blue oxygen, okay? You probably can't tell it's blue, but I can see that. If I went and said, and I'm doing all the same work, all the same formal charges would apply, everything looks good here, and then I tried to decide which one was the better Lewis structure, would it still be the top one? Well, now we've got the minus formal charge on oxygen versus the minus formal charge on nitrogen. Who's more electronegative? Find that nitrogen, find that oxygen on your periodic table, and you see that oxygen is further to the right, so oxygen is more electronegative. So when I've replaced the sulfur with the oxygen, suddenly this becomes the better Lewis structure. This one isn't. So with oxygen, it would be this one with a triple bond here and a single bond here, whereas with sulfur, this was the better Lewis structure. So that last rule, even though everything looked the same, shows me that you don't know what it is until you get right down to those formal charges and compare it to the periodic table and who is more electronegative. All right, so what's next? We've got all of that going. We did that. I think what's next is we're going to use our formal charges to help us with connectivity next, okay? So that's the second thing we can do. Here we have exactly the same connectivity and we're deciding which one's better. Let's draw a line through here and let's work in this space over here and let's see which one is going to have a better connectivity. When you see CH2O, you don't know if the C and the O are both in the middle and the hydrogens are on either side, or maybe the hydrogens are both connected to the carbon and the oxygen is also connected to the carbon. So let us see with the connectivity and formal charges which is better. So we have H, C, O, H as one of them, and we have H, C, H, O, and I'm putting lines in there and I shouldn't yet. Okay, we have H, C, O, H for this one. Now both of them have the same atoms, so both of them are going to have the exact same electron count. So let's do an electron count. We've got carbon with 4, we have oxygen with 6, we have 2 hydrogens, they're each 1, so that's 2 more, and that's 12 electrons to work with in both cases. So I have 12 to work with. My rules say to connect everything with a single bond first, 2, 4, 6. Go out and work your way in. Hydrogens are can't have 8 electrons, so I can't do anything there, but I go 2, 4, 6, and I'll go here 8, 10, and then 12, and I have to stop. This carbon's not happy, so I'm going to shift. So I'm going to take these 2 guys here and shift them in. Now I've used 2, 4, 6, 8, 10, 12 electrons, and everybody has 8. Let's stop with that one for a little bit, and let's go to this one. Connect everything with single bonds, 2, 4, 6. Go to the terminal atoms, the outside atoms, and give them 8. Well, hydrogen doesn't get any more, so we go to the oxygen. 2, 4, 6, 8, 10, 12. Okay, so I've used all my electrons, but my carbon is not happy, so I'm going to shift. So I'll take 2 of these electrons and shift them in. They still belong to oxygen, but they're being shared with carbon. I have used a total of 12. Let's double check. 2, 4, 6, 8, 10, 12. I've used 12. And everybody has 8. So there's its Lewis structure. So we have Lewis structures, and now we're going to use formal charges to decide which Lewis structure is better, and then help us know which way is this really connected. All right, hydrogen has 1 electron off the periodic table, 1 per bond, okay? Hydrogen will always have a 0 formal charge because I'm only going to let you do a single bond to it and nothing else. Go to carbon. Carbon has 4 off the periodic table. We count the lone pairs, 1, 2, and 1 per bond, 3, 4, 5. So I'm going to subtract 5. That's a -1 formal charge here. We go to this oxygen, 6 off the periodic table. 1, 2, 3, 4, 5. We subtract 5, and that's a +1 formal charge, and hydrogen is a 0 again. So all of these do add up to give me an overall charge of 0, which they are supposed to do because that is a molecule that doesn't have a charge. Now let's do it for our other compound. We have hydrogen, 1 minus 1. It has a 0 formal charge. Okay, single bond hydrogen always does. We go to the oxygen, 6 off the periodic table, subtract 1, 2, 3, 4, and 1 per bond, 5, 6. So I'm subtracting 6, so it has a 0 formal charge. Then I come to my carbon, 4 off the periodic table, no lone pairs, subtract 1 per bond, and I'm subtracting 4. So everything in here has 0 formal charges. That's the best. So I can, between these two, realize that this is really how they're connecting. They're not connected this way, they're connected this way. So that's how we use formal charges to determine connectivity. Whereas over here we have the same connectivity, we're using formal charges to help us know which one's the best Lewis structure of those. All right, so that concludes our lesson on formal charges, how to calculate formal charges, and what to use formal charges for.